Do nucleophilic substitution reactions, and the large part of this activity and lab is to get you to evaluate the individual pieces and kind of self-discover the important aspects of the reactions and how we can design and build individual experiments. Okay? So before we start, what we're going to go through and do is look at an individual reaction and try and decide what things changed. And this is what you should do for every single reaction you ever see. Identify the bonds broken and the bonds formed. So if we could go ahead and take a look at this, let's find the bonds that are broken. What bond is broken? Where's the easiest place to look, or where's the best place to look for the bonds broken? And the reactants. And what we'll do is compare those to the products to see what changed. Okay? And so in this case, I heard a lot of people referring to it by its full name, that carbon LG bond broke. Okay? So we could identify that. What bond was formed in the course of this reaction? Where's a good place to look for that? We'll look for that in our products, and we've got the carbon NU bond that is formed. Okay? So if we're going to go through and try and describe this reaction, we can say we did a substitution. The LG was substituted for the NU. Okay, so that's our general term for it. The next part is trying to figure out, now that we know what's happened, how did it occur? What are the possible ways that we could get this reaction to occur? And this is usually a bit more difficult for students to figure out, so I'll give you a starting point to look at. The first possible way to organize this is to say we break the, I forgot my pen today, break the LG bond, then form the NU. Wow. I didn't realize how nice that pen was. Okay, what's another possible way that we could do this reaction? Okay, so we're looking at the possible ways that we can organize breaking the bonds and forming the bonds. So in the first case, we said we'll break our LG bond, then form the NU. How else could we possibly do this? Let's form, then break. As a big hint, can you guess how many options there's going to be? What's the last one? Then break. Can I fit this in here? Our last possible option would be all same time. Okay? So let's look through those three possibilities. All we've done is kind of just compared. Said these are the things that have to happen. We're not concerned about any chemical properties yet. We're only just saying these are the possible ways it can occur. Any one of those possible ways impossible. Is it not physically possible to do that? That's the question.
Oh, I was going to.
Are you going to answer? Go ahead.
To form the NU and then break the LG.
Good call. That last one, forming the NU bond and then breaking the LG, is not physically possible. Why is it not physically possible? If we go back and look at that and we form the NU bond first, how many bonds would that carbon then have? 5. Can we have a pentavalent carbon?
No.
No. Which means rule 3 is not a possibility. What we'd be looking at is positions 1 and 2. And yes, that 5th bond, for those of you that didn't see it, is hydrogen. Okay? Hydrogens are going to come back to haunt you when we move into elimination reactions. Okay? So remember that they are present. We do imply them. And if you have difficulty seeing in the line angle structures what's changing, go through, draw in every single atom. You'll probably do it 4 or 5 times before you get sick of drawing all of them, and you'll remember your hydrogens. Okay? So now that we understand how it can happen, what we'll go through and do is address or draw out arrows to describe it. So provide a mechanism. So in the first case, we said we broke the leaving group bond first. Okay? In this case, I'm changing the leaving group, or the LG bond, sorry, to an X, atom X. Okay? How can I show that that bond is breaking? What's that? Okay, I could draw a line through it, except now we're doing a mechanism. I want to use curved arrows to show the flow of electrons. So we can compare in that first step what things have changed. Carbon's lost an electron, that X gained electrons. So what arrow would I add to my structure? I show an arrow coming from that bond. The electrons in that bond went to atom X. In the process, atom X gained electrons. It's now negative. We took the electrons out of that bond, so what happened to the bond? No longer there, so we don't draw that line anymore. What happened to the carbon? Lost electrons, so it's now positive. Okay? So there's our first step. The next step of our reaction was to form the Nu bond, the carbon Nu bond. So how can we show that bond forming? We can add another curved arrow from the Nu to the carbon. Why does the arrow start at the Nu going to the carbon? We have to show the flow of electrons, and does that carbon have any electrons? No. How do you know that? It's positively charged. Okay? So our Nu has to supply the electrons. What's something that you could look for that would be a red flag that Nu has electrons?
Negative charge.
You could look for negative charge. It's not charged in this case, so what else could you look for? You could look for non-bonding electrons, okay, or a lone pair. And what we've done in this case is now created our product. Okay? If we move to the SN2 mechanism, we said that all happens at the same time. So I have to form the carbon nuclear or Nu bond first. How can I form that? How would I show that formation? So if we're going to show the flow of electrons, where should we start the arrow? Why at the Nu? How do you know the electrons are there? The negative charge. So we can show our electrons flowing towards that carbon, which means we're forming a bond, which would mean we've got too many bonds on that carbon. So we're going to have to do something to fix that in this step. We'll break the bond between the carbon and X. So all of the arrows happen in one single step. We've now got our SN2 reaction. Okay? Make sense? Okay. We can now go through and identify what all these weird symbols were. To start off with, we'll go through and look at the Nu. Nu is your nucleophile. Okay? We already came up with some terms for that. Why would we say Nu is a nucleophile? Why is that a good term or symbol to use? Nucleophile starts with Nu. Okay? So we're trying to come up with something as general and simple as possible so that we can apply it quickly. Okay? The nucleophile has to be able to donate electrons in this reaction. We just came up with some things that could explain that. Negative charge. It has extra electrons, or it has so many electrons that it's negative. Okay? The other thing that we could look for are just lone pairs. Okay? Another part that's important to this is your substrate. Okay? Your substrate is found in the reactant. Okay? And you'll notice that that substrate has the leaving group attached to it. Okay? So what we can go through and do is evaluate the carbon in the substrate where our leaving group is attached. Okay? In this case, what can you tell me about that carbon? It's sp3. What else could you tell me? Has a hydrogen attached to it. Good. Keep going. It has a carbon attached to it. Yes. It has two carbons attached to it. So we could classify it?
Neutral.
Yeah, it's neutral. How about secondary? So we can classify the carbon in this case as an sp3 carbon that is secondary. So it's just adding some information about it. So we're trying to come up with some way to classify that substrate structure. We'll then want to compare that in other reactions. The other parts that are important in this reaction, which we're not going to evaluate in the experiment, you've got your solvent. Okay, we haven't shown anything about the solvent yet. That's going to show up in your group activity. The solvent is going to push one mechanism over another, depending on what that solvent can do. The intermolecular forces from that solvent will affect the intermediates in those reactions, changing which one is favored. The last thing that we're going to evaluate is your leaving group. The leaving group you can see much more clearly in the product because it's what is left. It's typically negatively charged because it took electrons, but it doesn't always have to be. Okay? And that's the group that was replaced in your substrate. Okay? Make sense? So as far as your experimental substitution reactions go, we're going to run two different experiments. Okay? But because they're related to each other, we're running them all in the same day, and they also go really fast. Okay? So treat each of these as two independent experiments. So we'll run the SN1 type reaction. And in the SN1 reaction, we're going to start with some substrate, and we are going to react that. What color was our nucleophile?
Green.
Thank you. With a nucleophile, which in this case is right here. Okay. How can we tell that was our nucleophile? If we look to our product, there's the piece that was substituted in. You'll notice what I circled as our nucleophile is not exactly what I circled over in our product. There's a hydrogen there. So if I'm going to ask what the nucleophile is in this reaction, do I have to specify the hydrogen? What did I add to the reaction? I added it with the hydrogen, which means we have to include that as part of our nucleophile. Okay? One of the secondary steps not shown in the reaction is the loss of that hydrogen. It is removed. Okay? Also, the other interesting thing with the substitution reaction that's going to help push it as an SN1 is our solvent. What color was our solvent? Is that red?
Yeah.
Our solvent is added at the very beginning. In this case, our solvent also happens to be the nucleophile. It's one of the or something that is often the case with SN1 reactions. Your nucleophile is often the same thing as your solvent. Okay? This solvent pushes for the SN1 reaction as far as determining if your reaction actually occurred. So far, all we've looked at are the pieces that allow for the substitution reaction. Okay? You can't see this reaction physically occurring, so we need some way to visualize it. That visualization is going to come in the form of the precipitate. So if you see a solid precipitate form in your reaction, that is a red flag that that reaction occurred. Okay? So when we see a silver X precipitate, we know we've got a reaction. Where did that X come from? Our substrate, which would suggest that we actually did the substitution reaction. X, in the case of your experiment, one of them is going to be chloride. Okay? How common is the chloride ion? Really, really common. Okay? Why is that a problem? If I just add sodium chloride to this reaction, what's going to happen? Sodium chloride will dissolve. The chloride then does what? Attaches to the silver ion. What do we see? Precipitate. Does that mean an alkyl halide substitution occurred? No. Okay? So one of the problems with the SN1 mechanism is false positives. Okay? So that's an issue that we're going to have to address. When we move into the SN2 conditions, okay, we'll go through and address each of these same ideas. Where's our nucleophile? So now the question is, what is it? Is it I or NaI? So we added NaI, but what happens when I add NaI or sodium iodide to the solution? Well, let's not even look at the product yet. What kind of bond is between sodium and iodine? Ionic. Is that a strong bond in comparison to a covalent bond or a weaker one? In comparison to a covalent bond? Which dissociates when you add it into water? An ionic bond or a covalent bond? Ionic. Which one's stronger? Covalent. When we add sodium iodide into the solution, what happens? It instantly dissociates. Which means, what do I have? I have an ionic bond, and what I've got in solution is iodide. Okay? So what's the active nucleophile? It's iodide. It's I- in this case. Okay? We couldn't separate our ethanol molecule because the bond between the oxygen and hydrogen was polar covalent. That's a much stronger bond. It doesn't immediately dissociate in solution. Okay? What's your solvent? Solvent in this case is acetone. That solvent is going to stay constant within the SN2 reaction. So we're always going to use that same solvent, and that's going to push our SN2 mechanism. As far as what we visualize, we see the sodium X as a precipitate. What did I say in the first case that X might be? Chloride. Sodium chloride. What can you tell me about it? It's water soluble, which means how do we see a precipitate if it's water soluble? You don't. But we do see a precipitate. Why do we see a precipitate? Nope, it is NaCl. What's our solvent? Is that water?
No.
No, there's where our issue is. We see a precipitate because there's no water. So what's the problem with the SN2 visualization technique? If there's water present, do you see a salt form? No, you get false negatives in the SN2 reaction. Okay? So with all of these possible things messing with your results, we're going to need to come up with some way to average these out. And that's why your TA is going to write up on the board some version of this table. And as you complete your results, you'll summarize your individual results on the board, and then we'll average those out at the end. So if for some reason your glassware was dirty and say had a little bit of chloride in it, okay, and every single reaction you got was a positive for the SN1 reaction, we can now account for that mistake by averaging it with the rest of the class. Okay? Last thing before we put you into the group activity, we want to go through it and evaluate what things have changed. So let's take a look at our leaving groups. Okay? Our leaving groups happen to be atom X. Okay? What did atom X need to do in the reaction? Go ahead and pass that out. It had to take electrons away from our substrate. What kind of a species would take electrons from a carbon? An electronegative species. What's your classic electronegative species? Oxygen works. I like the fluorine, chlorine, bromine, iodine. Your halogens are great leaving groups. They will take the electrons very easily. So if we go through and look at each of our substrates, what do we notice? Bromine, chlorine, bromine, chlorine, chloride, bromide. We're looking at chloride and bromide as our leaving groups. If I wanted to see the leaving group ability in any one of these reactions, let's compare those first two reactions. Not quite yet. Let's take a look at the substrate next. Substrate's referring to the number of carbons. Do we change the number of carbons during our reaction? Butane, butane. Butane, butane. That would suggest they're all the same number of carbons, but if I change the structure, 1, 2. I am changing the substrate structure. So if we compare experiments 1 and 3, the substrate structure does change. Okay? So you could go through and classify what your substrate is, define it, come up with some way to compare between them. So why is this important? If we compare experiments 1 and 3, what are we going to test for? What's the only thing, sorry, 1 and 2. What's the only thing changing between experiment 1 and 2? The chloro versus the bromo, which means what am I going to be testing for? What could I find out by a reaction changing? The activity of the leaving group. How good was that leaving group? Because that's the only thing that changed between those two experiments. What if I compare the experiments 1 and 3? What's the only thing that's changed? The location of our leaving group, so we're changing the substrate. So we very carefully limit and control the different variables within our experiment to try and predict and determine what's happening in each of our reactions. Okay? Go ahead and work on the group activity. If you've got questions, raise your hand. Raja and I will be by to help you out.